All right, let's keep going. We were talking about the thermal efficiency of a heat engine. That's always going to be what we want. The net power output divided by what we have to do to get it. That's the heat input. This massages down into this expression 1 minus Q dot L over Q dot H. And the maximum efficiency, maximum thermal efficiency, the ability of this thing to convert heat into work is the thermal efficiency. The highest value that can be is if I take the ratio of the low temperature divided by the high temperature. The temperature at which this heat is being moved in, so whatever the heat source is, the temperature of that heat source, that's my divide, the bottom of the quotient here. On the top of the quotient there is the temperature with which we're rejecting heat to. So the maximum efficiency for this device is determined by those temperatures. Right? And that's based on Carnot principles, and that's true for any reversible heat engine. Okay. And we could also encounter a refrigerator or an air conditioner. Right? An air conditioner is a type of refrigerator. So a refrigerator, kind of the reverse of that. We run this device in reverse. The goal of the refrigerator is to lose heat to a high temperature source, and here we run a refrigerant of some kind through a condenser. That condenser is fed by some kind of a compressor. I like to draw mine in the turbo format. So I've got a power input. And in the condenser, the bottom side, the low pressure side, is what we call the evaporator. And that's where we're going to gain heat. We're going to remove heat from the low temperature source. The evaporator is fed by this magical, wonderful device we call an expansion or throttling valve. We don't have to worry too much about that in this course. Basically, if we can achieve anywhere close to supersonic flow right here at the choke point, magic things happen. And the basic idea is the pressure from here to here will drop, and as the pressure drops, so will the temperature. We get really low pressure or low temperature on this side of the expansion process, and the temperature of the refrigerant is so cold that now it will remove heat, or it'll absorb heat. When we run it through a heat exchanger, it'll absorb heat from the low temperature source. So the power input is equal to Q dot H minus Q dot L, basically the net heat out. And we measure the performance of this device, COP for the refrigerator. Again, it's what we want. In this case, it's Q dot L. Divided by what we have to do to get it, that's the work or the power input. This can be massaged down using this expression, plugging in here for the work in, and divide everything by QL, looks like. That's 1 over Q dot H over Q dot L minus 1. And these can be dots, or if I know the amount of time this thing's operating, it can be total amounts. They don't have to be per unit time, they can be per unit mass. You've seen that throughout all the semester. That's one of the first, thermo is one of the first places we teach you. Look, you can work things per unit time, you can work them per unit mass, you can work total amounts. It just depends on the information you have. So I'm drawing dots on these, but if you have total amounts, if I've got joules instead of watts, you could work this without dots on it. Okay? All right, the max. The best this refrigerator can be is if it's reversible. And the reversible refrigerator's performance is determined by the temperature of the bodies that it is moving heat between. Just like with the heat engine, right? And we saw that with the second law, which is where we're headed. I'm not going to talk about a heat engine here. One of these two will show up. And if it is a heat engine, you've seen a heat engine before. You've actually been tested on a heat engine. Okay? So a heat engine is very similar to a refrigerator. You'll be just fine there. Okay. So let's talk about the second law. All right. So we talked about properties of substances. We've talked about compressible systems. We've talked about the first law in depth. We're working our way up to the second law. We've talked about the goal is to be able to use the first and second law in problems. I'm going through the learning objectives in my head here. And the last one is the ideal cycles. And here we've got ideal cycles here. Okay? All right, so let's talk about the second law. In its purest, rawest, ugliest differential equation form, the second law says that an entropy change is always going to be greater than the amount of heat that causes the entropy change divided by the temperature at which that heat transfer occurs. This is essentially the conclusion that our good friend Klaus has reached when he's trying to get the best efficiency out of his steam engine or out of his heat engine that he possibly can. Now, if I integrate this equation on both sides from state 1 to state 2, if I integrate ds, I just get delta s. And why would I integrate it? Well, because I'm not assuming you've had differential equations yet, and let's see if we can get this to a not differential equations form. And this isn't even an equation. This is an inequality, Steve. I know. Sorry. Let's see. So this is big S, by the way. This is total entropy. So if I integrate both sides of this from state 1 to 2, integrating ds, that's delta S. S2 minus S1 is going to be greater than the integral from state 1 to 2 of all of the heat that occurs to get from state 1 to 2 divided by the temperature at which those heat transfers occur. So take every little tiny amount of heat transfer that occurs to get you from state 1 to 2, divide every amount of heat transferred by the temperature at which it occurs, add the heat in, subtract the heat out. That's what the integral is telling us, is add up a whole bunch of little tiny slices. So every little tiny slice of heat transfer, add the ins, subtract the outs. That will give you a quantity. That quantity represents the entropy change, is kind of the expected entropy change. The Klaus's conclusion is that that entropy change is always greater than the heat transfer that causes the entropy change. This is very important. This quantity is always greater than this one. The reason that's important is because that tells us something is happening, something very important is happening. And what we normally do is, rather than write this as an inequality, we just acknowledge what's actually happening. We say, well, as you add up all the heat to get from state 1 to 2 divided by the temperature, you get a bigger quantity than when you started. What that means is something's being generated. Entropy is always being generated. The entropy generation is always positive. Again, if you find a situation out in the real world, if there is such a thing, where you think you've destroyed entropy, call me. Do not tell anybody else. Call me. We're going to make lots of money if you can figure out how to destroy entropy. To the best of our knowledge, we do not think we can destroy entropy. Negative entropy generation would be entropy destruction, and we are pretty sure that's impossible. That's why we call it the second law of thermodynamics, not the second theory of thermodynamics. Everything points to this as truth. Okay? So, this is the rule. This preserves the inequality. Right? So we can write this as an equation. This is the second law, how we typically present it for a process from state 1 to 2. If I divide by mass, then this becomes little s2 minus little s1 is equal to the integral from 1 to 2 of del little q over t plus little s gen. I can always work this per unit time. If I want, I can say m dot times s2 minus s1 is equal to the integral from state 1 to 2 of del big Q dot over T plus big S gen dot, where all those are per unit time. So entropy is always energy. This is energy per temperature. So these are energy per temperature. If I divide by mass, this is energy per mass per temperature, because this is energy per mass per temperature. So these are energy per mass per temperature. This is energy per time per temperature. So this is energy per mass per temperature multiplied by mass per time. This whole thing is now energy per time per temperature. Okay? I know, it's kind of confusing, but you get through fluid mechanics, you'll have a little better appreciation for understanding. Is it per time? Is it per mass? Which is it? Anyway, this is the second law. Right? It can take a number of forms. This is the second law for a process from state 1 to 2. Any three of these are okay, as long as you abide by this rule. If you have something that doesn't abide by this rule, we think that's impossible. Okay, page 8. Okay. All right, what else here? What do we do with this? Well, what the heck do we do with this? Well, let's talk about the right-hand side. If I have something that tells me that I'm dealing with a reversible situation, right? The best case scenario. If something in the problem statement tells me enough that I can assume I'm dealing with a reversible situation, that's this best case scenario. We're saying Sgen is always positive or at least 0. We're saying the best scenario is when it's 0, when entropy is conserved. We don't generate any new entropy. So what do we do with this Sgen? Well, it's either going to be 0, or it's what we're looking for, or in a really weird case, maybe we know the amount of entropy that's being generated and we just plug it into the equation. Those are kind of my three options. It's either this guy's either going to be 0, in a weird case it might be known, or it's what we're looking for. Okay. If it's what we call adiabatic, man, that's easy. If it's adiabatic, this weird partial integral just goes to 0. That makes things simple, right? If this is 0, these are table properties, and then I'm probably just looking for this guy, unless I know this is 0. If this is 0 and this is 0, then I know delta S is 0. We call that isentropic. Okay? So adiabatic plus reversible. And again, I always draw an arrow here. This is not, I do not draw an equal sign here. This is an arrow. If you know these two things, then you know it's isentropic. That means S2 is equal to S1. By the way, when you're taking a test with me, don't just write S2 is equal to S1. Right? S2 minus S1 is equal to this integral del Q over T plus Sgen, and then cross these out. You don't have to. If it is truly isentropic and you just, as long as you write this somewhere, I'll be okay. I would prefer to even see this. If you write this and tell me then this is what it means, awesome. If you just say, if you don't acknowledge anywhere why you know S2 is equal to S1, if it's not correct, I cannot help you with partial credit. Does that make sense? If you write this out, even if this is not correct, I can say, oh, that's why you assume this is isentropic. That's not entirely correct, but I can at least give you partial credit for your second law. If you don't write this, you don't write this, just it's like it's not at all clear why you're making this assumption, I cannot promise you any partial credit on the second law portion of the problem. Okay? If you'll show me you understand why it's isentropic, because it's possible you're not correct. So if you'll show me you know why it's isentropic, that really helps both of us out. Okay? This shows me you know why it's isentropic. Write this out for me, please, if this is true. Okay. If heat transfer occurs at a constant temperature, maybe an average temperature, right? Then this integral of Q over T, and many texts will present it this way. They'll just say add up Q net in divided by the temperature. So add up all the heat in divided by the temperature that it occurs at, subtract all the heat out divided by the temperature that those heat outs occur at. Most of the time you just have one heat. Right? Most of our problems, if I'm an introductory thermo course, we don't have to worry about going around the entire system and figuring out everywhere heat transfer occurs. We just got one heat going. We just need to know whether it's in or out. That's going to determine the sign here. Okay? So these are kind of the three things that I can do with the right-hand side of the equation for us as an introductory thermo course. This is either 0 or we're probably solving for it. This is either 0 or it's Q in divided by T or minus Q out divided by T. Those are kind of the main scenarios that we can see. You've seen that on the exam. You've seen that in the homework. Nobody's asked me questions about it, so I'm assuming you're doing okay. If you're not, tell me. I don't know you're not doing okay with it if you don't tell me. I got to stop there. We'll pick up the next one.